Okay, so we're going to start the first part of chapter 2. I just want to do a little bit of this because that's all we would have had time to do in class today. And so I'm just going to go through the first few slides and that is it. So when I get too far behind. So this is a chapter objectives. Again, I'm not going to read through them, but when we do get done, you should be able to go through them and say, yep, I can do this. Yes, I can do that. So these are the important things, the takeaways you should get from chapter 2. Here are your vocabulary words. And then we're going to break this down into 4 sections. So you're going to see my Canvas site set up with 4 parts to chapter 2. So we're going to start 2.1 today. So the chemistry of life. Most biologists actually have a chemistry minor because we have to have so much chemistry to understand biology that you have to take like 1 additional class to have that minor. So what is matter? So matter is anything that occupies space and has mass. Matter, I love this. It exists as one of 3 states, and that kind of cracks me up because actually there's 5 states of matter. And you guys are all familiar with solid, liquid, and gas. A solid has a specific shape, and I'm going to close my door here, and a specific volume. A liquid has a specific volume, you know, so you have if you had a liter of liquid, it doesn't matter what container you pour it into, it will have that same volume, but it will take different shapes. Now a gas will, hold on here. Hello, I'm recording right now.
No, it's okay. I'm just taking trash.
Okay, thank you. A gas has no specific volume or shape. So a gas will occupy the complete shape of that particular container. And so we have the law of conservation of matter, and that is matter is neither created or destroyed. It only changes form. So I know, like, for instance, when you burn that gasoline in your car, it doesn't just disappear. It's being used for converting from potential energy to kinetic energy. And we'll get into all that. On the side note, I tried to record here at school because I figured I wouldn't be interrupted. And yeah, you can see how well that worked. All right, moving on. Matter may be changed. So again, kind of like what I was talking about, physically versus chemically. So physically, we do not change. And I love to do this. I'm gonna actually do it right here since I have the ability. All right, so hold on, let me grab something. So. And I'm going to switch so that you guys can see me a little bit better. So I'm going to stop sharing the screen. Okay, so when we talk about matter changing form, so for example, I can take this piece of paper and I can tear it into pieces and it's still paper. It's just a different shape. Okay, so there's my paper. So it still has all the characteristics of paper. I can write on it. I can test it with iodine, it'll turn black and all that good stuff. Now, I did not break any of the chemical bonds inside that paper. All right. If I do some chemistry here, which I'm going to, I am going to burn the paper. So if I burn the paper, I am breaking chemical bonds inside that paper. All right. I am changing the characteristic. I got to make sure I don't run out of oxygen. I am changing the characteristic of that paper. It is no longer paper, right? It's ash. We've released carbon dioxide, we've released energy. I can try to get the whole paper burned, but I didn't. So that has to do with breaking chemical bonds. That's physical. That's chemical. Okay. It's kind of cool. I like to do a bunch of little demos, but we can't do them when we're at school, but I can do them here. All right. So I'm going to go back to sharing my screen. All right, elements. So elements, they are the fundamental units of matter. So with those elements, we cannot break them down. We can break them into smaller things. We can talk about atoms and subatomic particles, but once we break them down smaller, they start to lose their specific properties. And so elements are the smallest unit that contains, I mean, we can break an element into single atoms. Each element is made up of a specific type of atom. But once we go further, if we break that atom down, we start to lose those properties. So here are a couple of elements. So elements will all be found on the periodic table. Here is hydrogen and helium. We're going to use a symbol, H for hydrogen, He for helium. They are usually with 1 or 2 letters, of course, because they both start with H. So we have to put the second letter in so we know the difference. Some of the elements you may have noticed that like make absolutely no sense. Like potassium is with a K. It's actually kalium, or sodium is natrium. They are named after their Latin roots. All right, so we go back to Latin with that. So the elements are the fundamental units of matter. 96% of the body is made up of just 4 of those elements: oxygen, carbon, hydrogen, and nitrogen. And we're going to talk about all those 4 elements a lot when we get into biochemistry. And so again, when we look at our periodic table, here's kind of the percentages here: life, the atmosphere, and the Earth's crust. So a lot of people think that most of the atmosphere is oxygen, and in fact, it is nitrogen. So we can look at these percentages. It's kind of interesting. We have trace. We talk about carbon. I don't know why they put trace for atmosphere. I'd really be curious to know how much CO2 is. But again, it's a comparison, right? There's a lot of elements, a lot of atoms that make up our atmosphere. So I guess when you consider that nitrogen 78% and oxygen is 21%, the rest is all kind of left over in smaller amounts. When we look at the percentages in the human body, here you go. You can see the oxygen, carbon, hydrogen, and nitrogen. Then we get into really small, what we would, call our minor. We got our major elements, our minor elements, I guess: calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. And then we have trace. Trace means they're very small, but they are very important. For instance, selenium has been known to cause a lot of different physical ailments for individuals in Japan after the atomic bomb. The atomic bomb pretty much deprived the soil of selenium. And so they were taking supplements to help get that element back in their body to prevent some of these particular health issues they were having. Oh, if I go back, iodine, you guys know iodine's important because without iodine, you get a goiter. It's where your thyroid starts to grow out of control, which is why you take an iodized salt. They've added iodine to that for you. And then we have the structure of the atom. And with that structure, we can see we have the nucleus. The nucleus contains neutrons and protons. And then we have the outer orbital, which has the electrons. The proton, if we talk about the protons, protons have a positive charge, electrons have a negative charge, and neutrons are neutral, so they have no charge. The mass, when we talk about atomic mass unit, we can also talk about it being, we call them AMUs or sometimes Daltons. A proton and a neutron is approximately the same. They're equivalent. An electron is not massless. It's so small. We pretty much say it doesn't have much mass. But if it didn't have mass, it wouldn't be matter. And then we would have a conundrum there. But it does. But it's like, I don't know, like 10 to the negative, like 20 some power. I mean, it's really, really, really small. So like we said, the proton and neutrons are in the nucleus and the electron is in the outer orbitals. Now, this is where a lot of students struggle. The atomic number refers to the number of protons in an element. I would highly suggest you getting a periodic table. With that periodic table, you need to be able to look at it, and I'm going to go through the periodic table with you in person next week. So you need to know which number, and I'll kind of give you a hint. You cannot have partial protons. So the whole number, and I know that Liz has all whole numbers here, but if you actually looked at a periodic table, you would notice that the atomic mass of carbon is not just 12, it's like 12 point something, something, something. Okay. So the 6, when we talk about the 6, that is the number of protons. The number of protons will not change within an element. If you change the number of protons, you change that element. The mass number, that's like how much does it weigh? That is going to be the number of protons and neutrons. Because remember, we said that a neutron and proton both equaled 1 AMU. So what I'm saying here is that carbon has, and we'll talk about my PEN or pen. We'll do that in class on Monday. So you need to tell me, if I give you an element, you need to tell me how many protons, how many electrons, how many neutrons. And then we also have this thing called isotopes. Now, isotopes, they have the same number of protons, but they have different numbers of neutrons. And so their masses are different. And in some cases, those neutrons, like the neutrons are in there because you know that like if you have two positive charges, they repel. Okay. This is a problem. It's like having two magnets and you have both north ends and you know they repel and you flip it and then it attracts. Well, we have that same problem going on in an atom. You have this little tiny nucleus packed of positive charges and they're not going to be happy. They are going to repel each other. So we have to throw those neutrons in them. I call them the peacekeepers. And so the peacekeepers get in there and they keep them from repelling. They keep the nucleus intact. You also have the electrons. And remember, the electrons, they also have negative charges. So they will spread out in that outer orbital to maximize their distance between each other. But they will have two issues. One, they want to maximize the distance between each other because they repel, but they also want to be close to the protons because they're attracted to the opposite. And we'll talk about how we can organize an atom in order to maximize the distance between the electrons and minimize the distance from the nucleus. Some atoms have extra neutrons or less neutrons, and those are called isotopes. And so they have different masses. They will have the same atomic number, all carbon, whether it's carbon 12, carbon 13, or carbon 14, right? So they will all have 6 protons. If it doesn't have 6 protons, it's not carbon anymore. But they have different number of neutrons. And so that makes them weigh differently. And those are called isotopes. Many isotopes. So here is the isotope of hydrogen. Hydrogen is so special. Its isotopes get special names. So we get protium, which is normal hydrogen. I would say it is, you can't say it's normal. I would say it's the one that's most represented. We see this the most, it's most common. And that is where it only has 1 proton and 1 electron. It doesn't need a neutron, right? Because it's just 1 proton. But we have deuterium, which is actually related to, we see a lot of deuterium in the water around nuclear power plants. We call it heavy water because it has a higher mass because it's picked up an extra neutron. So notice we've got a proton and we have a neutron. And then we have tritium, and that's where it would have a mass of 3 atomic mass units. And so we would have we would still only have 1 proton, but we have 2 neutrons. Okay. And I don't know why she picked a different color for each of those. I would have put, kept my protons, the blue or seafoam green or whatever you want to call it. And then I would have kept the proton, neutrons purple. And then some of the stuff we do with carbon dating, you may have heard of that. Because carbon has different isotopes, plants take in carbon all the time through carbon dioxide. As they fix that carbon into their bodies, they can't tell the difference between carbon 12, carbon 13, and carbon 14. And that's all present up in the atmosphere due to all the chemistry going on there thanks to the sun. And so we know there's a certain ratio of carbon 12, 13, and 14 in the atmosphere. Carbon 14 is not stable. It will decay in about every 4,000 years. If you started off with 10 grams of carbon 14 in your body, once you are dead in like 5,000 years, you'll have half that. And then in another 5,000 years, you'll have half of that. And they keep going by halves. And that's referred to as a half-life. So we can take these different isotopes that we know their proportion in the atmosphere, and we can use this as scientists to do what's called carbon dating. And this is where I can't say, oh, this specimen was 6 years old when it died, but I can tell you that specimen died 30 some thousand years ago based on carbon dating. Okay, so that's what we're using isotopes for in paleontology. In the medical world, we use it. We a lot of times will use radioactive, because a lot of these isotopes are radioactive. We'll use the isotope of iodine. If you've ever had a CAT scan and they put a radioactive tracer on you, that is generally iodine. And so they can then use that to highlight areas in your body and be able to see that on film that they're trying to trace. They're radioactive tracers. Okay. So here is the periodic table. Real quick, I'm just going to show you here because notice here we have, can't put my pointer on it. We have hydrogen. Notice that there are 2 numbers in that box. The atomic number will always be the whole number because remember the atomic number, you cannot split. You can't have a half proton. The mass number will be in decimal. And you know that you get on this balance and you're not exactly 140 some pounds. You might be 140.2. Okay. Most of our balances now, since they're electronic, go out to the 10th position. So, and that's because we're taking an average of all the masses of the isotopes and their proportion in the atmosphere. And that's where we're getting the relative atomic mass. Now, I am not going to get any more into the periodic table. I love teaching the periodic table, but this is something I want to do in person, but I wanted to at least get this far. So hopefully you can read up to this point, up to the periodic table. If you don't have a periodic table or there's one here printed off, I would have that ready for class next week. I'd also make sure you have some paper and some writing utensils because we're going to do some practice with our protons, electrons, neutrons, our atomic mass numbers, calculating all that stuff. And then we're going to figure out how to do what's called Lewis dot structures. Hopefully this was helpful. And if you guys have questions, again, you can ask me next week, but that is all you have for today's virtual class. All right. Thanks. I hope you guys have a nice evening. And if you have questions, please let me know, and good luck working on your lab. All right. Bye.